All right, guys, so it's been a while since we've spent much time with limits, but we're going to really be getting back into them over the next couple of weeks and going forward. So a couple of new things a few new tools for you to use to make some of these limits a little bit easier to work through. So in the past, if I gave you a limit like this one, the limit as x approaches 2 of x minus 2 over x squared minus 4. The first thing that you were told to do was to try direct substitution, right? You plug in the 2. The problem here is I end up getting a 0 on top, which is no big deal. But when I plug it into the bottom, I get a 0 on the bottom. And that's not okay. So your next step would be to try to do something to rearrange the equation a little bit. So on this one, you would leave the x minus 2 on top, but on the bottom, you would factor that to be x minus 2 times x plus 2, so that your x minus 2's cancel. And then you're left with the limit as x approaches 2 of 1 over x plus 2. And then you would plug it in again. Plug in the 2, and you end up with 1 over 4. That would be your limit. That's the way that you did it before. When we were going to infinity, you would plug in infinity. You would try direct substitution. In this case, you could also look at the powers. I've got a x squared on the top and an x squared on the bottom. So when I plug in infinity, that x squared is going to overpower everything else. And what you end up with, remember when we did top heavy, bottom heavy equal powers, you ended up with a limit of -5 over 3 because you took the coefficients of those two x squareds that are on the top and the bottom. Now, a new tool for you to use. So when you plug something in, like when we plugged in this 2, when the first time I plugged it in, on top I got a 0 and on the bottom I got a 0. Okay, we call those indeterminate forms. So if you end up with, when you do direct substitution, if you end up with a 0 over a 0, like this, or if you direct substitute and you end up with something like infinity over infinity or infinity over negative infinity, if you end up with something like that, it's called an indeterminate form. And when that happens, we've got this new rule that we can use, L'Hopital. And what this says is the limit as x approaches a of these two functions, if that limit, when I direct substitute, is equal to 0 over 0, or if that limit, when I plug it in, is equal to infinity over infinity, then the limit of f of x over g of x becomes the limit of f prime of x over g prime of x. So if you do direct substitution and get 0 over 0 or infinity over infinity, you can take the derivative of the top, the derivative of the bottom, and take the limit of those values and try it again. So just to see this in action, back to these limits that we looked at before. If I plug in 2, this becomes 2 minus 2 over 2 squared minus 4, which equals 0 over 0. That's an indeterminate form, 0 over 0. So by L'Hopital, I can take the derivative of the top and the derivative of the bottom and just use the limit of that function. So I can take the limit as x approaches 2 of the derivative of x minus 2 is just 1. Now, don't do a quotient rule. You're taking the derivative of the top, and that stays on top. And you're taking the derivative of the bottom, x squared minus 4 becomes 2x. That stays on the bottom. This isn't a quotient rule. We're taking two different derivatives, okay? So now I'm taking the limit as x approaches 2 of 1 over 2x. So when I plug in my 2, my limit becomes 1 over 4, which is what we got before when we simplified the denominator, okay? Now, this infinity, when I plug in infinity for my x's, my top goes to infinity and my bottom goes, well, my top technically goes to negative infinity because of this x squared it being a -5. So that tells me that by L'Hopital, And I'm going to keep writing this whenever I use it, because on the free response part of the test, if I just suddenly say the limit as x approaches infinity of -4 minus 10x divided by 6x minus 1, if I don't acknowledge why I'm able to do that, I'm going to lose points, or maybe all my points. So by L'Hopital, since they're both infinity, I can take the derivative of the top, -4 minus 10x, and the derivative of the bottom, and then I can plug in infinity again. So when I do that, when I plug in infinity, I get negative infinity on top, infinity on the bottom. So I can use L'Hopital again. So by L'Hopital, the derivative of the top is -10. Oops, I better write this out all the way. As x approaches infinity, the derivative of the top over the derivative of the bottom. So when I plug in infinity, there's nothing to plug it into. So all I end up with is -5/3, which is what we got before, which is really why that rule is what it is, okay? So let's try applying this to a few other problems here. So the limit as x approaches -2. Now, don't just assume that you're going to be able to use L'Hopital. You've got to plug in the numbers and make sure you get 0/0 or infinity over infinity. Otherwise, you can't use this rule. I'm not going to take the time to do it on this one because this is a video that I don't want to be 45 minutes long. So when I plug in -2, I do indeed get 0/0. You'll have to take my word for it, or go ahead and plug it in yourself. You'll see that you get 0/0. So I can say that by L'Hopital, the limit as x approaches -2 of the derivative of the top, so 3x squared plus 2x minus 8 divided by the derivative of the bottom, 3x squared plus 16x plus 20. Now I direct substitute again. I plug in -2, and I get 12 minus 4 minus 8, that's 0 on top. And I get 12 minus 32 plus 20, I get 0 on the bottom. So I get 0/0 again. So by L'Hopital, the limit as x approaches -2, I can take the derivative of the top, which is 6x plus 2, divide that by the derivative of the bottom, 6x plus 16. And when I plug in my -2, I get what? -12 plus 2 over -12 plus 16, which becomes -10 over +4, which becomes -5/2. That would be my limit when I plug in that -2. All right. Now this one on the right, same idea. If I plug in a 1, I get 1 minus 2 plus 1, so that's 0. I get 1 minus 3 plus 3 minus 1, that's also 0. So by L'Hopital, I can take the limit as x approaches 1 of the derivative of the top, which is 3x squared minus 4x plus 1, over the derivative of the bottom, 3x squared minus 6x plus 3. And then I plug in my 1. 3 minus 4 plus 1 is 0. 3 minus 6 plus 3, again, is 0. So by L'Hopital, I can say the limit as x approaches 1 of the derivative of the top, 6x minus 4, over the derivative of the bottom, 6x minus 6. When I plug in a 1, I get 6 minus 4 divided by 6 minus 6, which becomes 2 divided by 0, which is a problem, right? I can't do that. This becomes, because I have a 2 on top and a 0 on the bottom, I don't have an indeterminate form anymore. I don't have 0 over 0. Now I have 2 over 0, so I can't use L'Hopital. That 0 on the bottom messes me up, which means that my limit is probably not going to exist. You can try factoring out. On the top, we could pull out, a 2 and get 3x minus 2. I don't think anything is going to change. We can pull out a 6 on the bottom and get x minus 1. 2 over 6 becomes 1 over 3. So I just end up with 3x minus 2 on top. And on the bottom, I end up with 6x minus 1. And again, when I plug a 1 into that, I get 3 minus 2, which is 1. And nope, that should be a 3 on the bottom, right? Because I've got 2 over 6 becomes 1 over 3. So I times the 3 inside. So 3x minus 3, not 1. Bad math, Mr. Reed. Again is 0. So there's nothing I can do. That limit's not going to exist. Now, you can check any of these you want on your calculator. Like this first one, if I wanted to check my work, and again, I don't want to spend too much time doing this, but if I do x cubed, actually, you know what? I'm going to pause the video while I type this in. Okay, so I type it into my calculator. I just made a fraction bar, put the top on the top, the bottom on the bottom. Now, I know that when I plug in -2, it's not going to work, but I'm interested in what happens when I get close to -2. So here's my graph, and if I look at the values that are close to -2, so like let's do -1.9999, I get -2.5 almost, which is -5/2, like I thought it would be. Right? That's what we thought it was going to be. And if I go to the other side of -2, if I do -2.001, I also get -5/2. So you can check your limits on this one. We could plug this in and check and make sure that that's what actually happens with the limit. And barring that I didn't make an algebraic mistake, we should still end up with that the limit does not exist. All right. Limit as x approaches infinity of the natural log of x minus x plus 1 over e to the x minus e to the x. So if I plug in infinity here, 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 and here, if I plug in that infinity, my top, this negative infinity, is going to overpower my infinity on the natural log. And this negative e times infinity is also going to overpower. So I end up with negative infinity over negative infinity. So when I take by L'Hopital, the limit as x approaches infinity, I can take the derivative of the top, so 1 over x minus 1, divided by the derivative of the bottom. So e to the x, the derivative is just e to the x, minus e. Okay, now when I plug in infinity, when I put it here, when I plug infinity into 1 over infinity, this becomes 0. So I end up with -1 on the top. And when I plug in infinity on the bottom, I end up with e to the infinity minus e, which just goes to infinity. So -1 over infinity, if I have a small number on top and infinity on the bottom, that approaches 0. So my limit would be 0. Now this one on the right, I like this one a lot. We get to do a lot of steps here. So the limit as x approaches 0, if I plug in a 0, the sign of 0 is 1. So this becomes 2 minus 2, which is 0. So I get a 0 on the top. The sign of 0 is 1 minus 1 times the, I guess the sign of 0 is 0, right? So it's not 1. 2 sine of 0 minus sine 2 of 0. That's just 0 minus 0, which is still 0. On the bottom, the sine of 0 is 0 minus 0 times the cosine of x, which is 1. Well, 0 minus 0 is just 0. So by L'Hopital, I got the limit as x approaches 0 of the derivative of the top. So the derivative of 2 sine x is 2 cosine x. The derivative of negative sine 2x is going to be negative cosine of x. Oh, not cosine of x, the cosine of 2x. But don't forget your chain rule. I've got to multiply by that 2 that's on the inside. So I'm going to put that in front. Divided by the derivative of sine of x is cosine of x. Then I've got product rule. The derivative of x is 1 times the cosine of x plus the derivative of cosine of x, which is negative sine of x multiplied by x. So that becomes plus a negative x sine of x, which is nice because I get cosine of x minus cosine of x. And then this negative just becomes a positive x sine of x. So I end up with the limit as x approaches 0 of 2 cosine of x minus 2 cosine of 2x, all divided by x sine of x. So now when I plug in my 0, this is the cosine of 0. My x value at 0 is 1. So this becomes 2 minus cosine of 2 times 0 is the cosine of 0, which is just 1. So this becomes 2 minus 2. So I get 0 on top. And on the bottom, if x is 0, 0 times whatever sine of x is, which is 0, I end up with 0. So again, by L'Hopital, I can take the derivative of the top and the derivative of the bottom. So the limit as x approaches 0 is the derivative of 2 cosine of x is negative 2 sine of x. The derivative of negative 2 cosine of 2x. Again, I'm going to have to do the chain rule and multiply this 2 out. So I'm going to go ahead and do that first. And then cosine of x, the derivative is negative sine of x, but I already have a negative in front of it, so this is going to become a positive sine of x. Divided by the derivative of our product rule on the bottom, so the derivative of x times sine of x, plus the derivative of sine of x, which is cosine of x, times x. So I'm going to put that x in front. Now I plug in 0. The sine of 0, my y value at 0 is 0. So this is all going to become 0 on top. So I get 0 on top. The sine of 0 is 0. The cosine of 0 is 1, but x is 0. So I end up with 0 on the bottom. So once again, I'm going to do L'Hopital's rule. So by L'Hopital. And I'm hoping eventually I end up with something that I don't get 0 over 0. Sometimes you don't. Sometimes, especially with sine, cosine functions, sometimes you end up just repeating the same function over and over again. Same with the e to the x functions. But let's try it at least one more time. I'm going to take the limit as x approaches 0. And I'm going to take the derivative of the top. So the derivative of negative 2 sine of x is negative 2 cosine of x. The derivative of, something's wrong. This is sine of 2x. I forgot the 2 on the inside of the cosine. There we go. The derivative of 4 sine of 2x. I've got to multiply the 2 out because of the chain rule. So I know I'm going to end up with 8 in front. And the derivative of sine of 2x is cosine of 2x. All of that divided by the derivative of sine of x is cosine of x. the derivative of x times cosine of x. So this product rule, again, means the derivative of the first one, which is 1 times cosine of x. And then I'm going to add that to the first one times the derivative of the second, which is negative sine of x. So this becomes negative 2 cosine of x plus 8 cosine of 2x, all divided by cosine of x plus cosine of x plus, let's see, x negative sine of x. Well, let's just make that a minus. That's the whole reason I'm rewriting this. Negative x sine of x. All right, so let's plug in 0. Cosine of 0 is 1, so this becomes negative 2. Cosine of 0 times 2 is cosine of 0, which is 1 times 8. That becomes 8. So negative 2 times 8. Oh, look, I've got a number on top. I got 6 on top this time instead of 0, or, well, I guess we've gotten 0 like every time, haven't we? So now I've got a 6 on top. Good. On the bottom, the cosine of x, again, that's 1, plus the cosine of x, that's 1, minus 0 times this is just going to be minus 0. So that's going to become 6 over 2, which means my limit is 3. I lucked into a nice number. Now, again, if I wanted to check this on my calculator, if I wanted to check if this really is a solution, I can go to y equals. I can make a fraction, or not if it's a solution, if it is my limit. So I've got 2 sine of x minus sine of 2x on the top. I'll let you watch me type this one in. It's not too long. And then sine of x on the bottom, unless you hit the wrong button, sine of x on the bottom minus x cosine of x. Okay, when I graph, I like this graph. It looks pretty cool. Just because normally you get all of this line repeating, but when you get in the middle, look what happens. My graph, as I go up towards 0, instead of hitting this, instead of going to infinity, it looks like I'm going to 3. Now, if I were to actually try plugging in 3, if I say what's the value at 3, or sorry, what's the value at 0, as I'm approaching 0, I'm approaching 3. So when I plug in 0, I don't get anything. Okay, when I plug in 0, I'm not getting anything up there. So something weird might be happening right at 0, but I don't care what's happening at 0. I care what's happening right near 0. So if I put in 0.001, I'm hoping that I get something really close to 3, and I do. And if I plug in something a little bit smaller than 0, I also get close to 3. So this 3 looks like it would be a good, solid answer. Now, a lot of people would have given up back here after 2 or 3 steps. You have to make that determination of how far you're going to go, because you're not always going to end up with a number. Sometimes you're going to end up in this repeating pattern, and we'll try and find an example of that to do in class. But moving on, I think we've got one more question. So the limit of, as x goes to infinity, of 4x squared minus 5x plus 2. So if I plug in infinity, on top, I end up going to infinity. And on the bottom, e to the 5x plus the natural log of infinity. So e to the 5 infinity. Again, I end up with infinity over infinity. So by L'Hopital, I'm going to take the derivative of the top and the derivative of the bottom. So this becomes 8x minus 5 on top. And on the bottom, I get the derivative of e to the 5x is e to the 5x, but then I have to multiply it by the chain rule, the inside, remember? So I'm going to put a 5 in front as well, plus 1 over x. So now if I plug in infinity, my top still goes to infinity. My bottom, this goes to 0, but this one still goes to infinity. So let's use L'Hopital's again, by L'Hopital, the limit as x goes to infinity, I can take the derivative of the top, which is just 8, over the derivative of the bottom, 5e to the 5x. The derivative of e to the 5x is e to the 5x, but I've got to do the chain rule and multiply that 5 down, and since I already have a 5 in front, that becomes 25e to the 5x. Plus the derivative of 1 over x. Actually, I better not write that plus because it's going to end up a minus. We can rewrite this as x to the negative 1. So you end up getting, you bring down the negative 1, so you get negative 1x to the negative 2. So that just becomes minus 1 over x squared. So now if I plug in infinity on top, I just get 8. There's nothing to plug it into. On the bottom, when I plug infinity in right here, this becomes 0. And when I plug infinity into this one, when I make this infinity, that actually goes to infinity. So if I have 8 over infinity, that is going to 0. I got a really, really, really big number on the bottom and a small number on top. So that's going to get closer and closer and closer to 0. That would be your limit.